Uh, Thanks a lot for joining in. This is Suraj, Course Director at Decibels, and I'm also one of the co-founding member at Decibels. So welcome to the webinar today, which is on auxiliary loads, electric vehicles. Quite an interesting topic, and not much talked about at many places. But when the range of the electric vehicle is being impacted by certain parameters, that is when things have sort of become more serious, because the load of auxiliary systems is very high at various different temperatures. It's dependent upon temperature, it depends upon various other parameters too. So that has brought up an interest to study, and it's not something as a very new topic, though a lot of publications are available, patents have been filed, and innovations has been done to do a system optimization, component development, a lot of architecture designs and things like that. So as a part of this webinar today, I will be addressing overview of these subsystems and to understand, maybe how much these systems can contribute, and what components comes as the part of the systems, which are auxiliary loads in EV. And then we would try to summarize, analytically in some points that, what kind of studies you should do to perform and understand the impact of auxiliary loads. So at the last, we'll try to conclude in understanding that, okay, this is what is the importance of auxiliary loads, and why somebody have to think very seriously about auxiliary loads if they're trying to develop an EV. Or in a case that, this could be also an extension to a lot of people, a lot of students, a lot of faculties and research scholars to perform, studies or develop activities of research in the areas of even auxiliary loads as such. Great. So with that note of interest, let me just start having the session. So what are auxiliary systems that are present in an EV? So there are multiple auxiliary loads that are present as a part of the EV. To define what is an auxiliary load, the load, the load which is not contributing to attractive output of the motor, that could be called as an auxiliary load. So there is something like a battery cooling and motor cooling that does indirectly impact the tractive output, because if the battery temperature is slightly higher, then you have different discharge characteristics for the cell. If you have higher temperatures of the motor, you have bad efficiency of the motor. Though they are impacting the system, but in an overall way, auxiliary loads can be the one which is non-contributing to attractive loads, right? So that can be defined as an auxiliary loads. So when we call as an auxiliary loads, these are the parts and components that come as a part of the auxiliary loads. We have climate control, so which you may be very well aware about what is climate control. It's like a HVAC system, heating, ventilation, and air conditioning. So it does two functionalities. One, we do cabin heating, right? So when we do cabin cooling. So country like India, we may not be very aware about cabin heating, but though in few places of the country where the temperature goes slightly below 20 or 15, you would have seen application of cabin heating, right? So cabin cooling is pretty common with increased temperatures nowadays. So then the battery cooling and the battery heating also is required, because when the battery temperature goes above specific value, the characteristic graph of the cell will be completely different. If you call this is a specific characteristic of a cell, a discharge characteristic of a cell, and this would be the voltage at this time. So if, let's say, this is for the temperature of 25 degrees Celsius, and if you subject the cell to go below a specific value, let's say 5 degrees Celsius, and you could see a complete drastic difference in its characteristic curve. So it becomes very important to ensure that the battery is maintained at a specific bandwidth. So we need to ensure that there is a battery cooling, and also there's a battery heating system that's supposed to be there in an EV. And then motor cooling. The parameter of motor cooling is important because the efficiency of the motor depends upon the temperature of the motor. And also the magnets that are used, which are basically permanent magnets, there will be a loss of magnetism if you expose this permanent magnet to a very high temperature continuously for a longer periods. So this would be sort of a lifetime effect, that once you ruin the characteristics of a magnet, then you will never be able to recover them back. So you have to ensure that the temperature of the motor is always pretty much in between the range. And if you see a country like India, we have a very varied temperature bandwidth, anywhere between, let's say, like 5 degrees Celsius, even up to 50 degrees Celsius. So if the ambient temperature itself is 45 or 40, for an example, the motor temperature at operation would be more than 60, 65. So it's very intensive to ensure that the cooling is there. We'll discuss what kind of cooling can be done, though the impact can be the demagnetization of magnets, and also efficiency of the motor will come down. So that is what can happen if you do not properly cool the motor. So if you cool the motor, then we have to depend upon some source of energy, right? That is going to be the batteries. So that is like an egg and chicken. So if you don't do it, then you lose energy. If you do it also, we lose energy, and we need to sort of find a trade-off that, where do you have to keep a system, and then that's what we do as a simulation engineers or a component development engineers. So find a right optimal point where you can actually match the system requirements and try to develop a commercially viable, manufacturable, repairable component. Right. So that's something coming back to the motor cooling. And then extensively, even the power electronic components, which is basically components such as DC-DC converters. And then we have a charger, and then motor controller. So all these components does require cooling because they're working at a very high switching rates and things like that. So you need to ensure there's a proper cooling for that. That requires energy. Then if you see, this is something till here as a heating and cooling energy, right? But also there are some other components which are electrical loads, right? Such as power steering. So if you have estimated the power steering, let's say you take a travel distance of 250 kilometers, like, if you take a Tata Nexon, imagine that it gives 250 kilometers of a range, that if you drive 250 kilometers, what is the percentage of energy that is being consumed by the power steering system, right? Because nowadays all the vehicles does come with power assist steering. So like that is again a contributing feature. Then we have a braking system. I'm not sure how many people have actually understood where do you use an electrical system for the part of braking. It's all hydraulic, what everybody understands, right? So but there is a requirement to create a vacuum. So we use a vacuum pump here, a small vacuum pump. So that's the involvement of a braking system. Then we have a lighting system that could be fog lights or DRL or headlights or any other lighting systems, even indicators, tail lights, your number plate light, a lot of these things. It looks very simple and very lower number, but if you consider them over a span of time, and that could be contributing too, right? Then your infotainment system, that could be your navigation, instrument cluster. It could be even in systems such as how would I say, music systems, or any of these systems would also contribute to the requirement for infotainment system. And then any other lower, any other systems such at 12 volt or a 5 volt, maybe your window regulators, for an example, or seating mechanisms, or recliners, height adjusters, right? Seat heating systems, whatnot, that is present in the part of vehicle, right? And even body control module, ECU, we have IoT devices in the electric cars today. A lot of these systems, they suck power, right? So we need to ensure that these systems need to be accounted when you think about designing a battery pack. Cool. So that's the overall systems. There are some more smaller systems too we can discuss down the line, but this is in a very overview way that what are the systems that are present in an EV as an auxiliary system, right? So if you have any questions at this point, I would be very glad to take it up. And just a comment from one of the participants that the audio is not clear. So Does everybody have a same issue, or is the audio been good for everyone? Right, okay, it sounds to be clear for one person. Okay, great. So Amol, just maybe check with the system at your place, our internet connectivity, so that would be the reason. Great. So I believe everything is going on great for everyone. So coming back to the discussions. So why is the estimation of auxiliary loads important? Okay. So I'll just give you a very, a very simple example that let's take an example of Mahindra E2, and the battery pack, they have like a P2, I think P4, P6, some of the models like this, right? So let's take that one of the model as a 10 kilowatt battery pack. Okay. So this is a battery pack size, right? So according to what Mahindra claims, let's say it gives up to somewhere about 120 kilometers range. Okay. So if you drain the battery from 100% SOC to 0% SOC, that's using a complete 10 kilowatt, you get about 120 kilometers of a range, right? So this is what is defined with certain constraints, right? So coming back to the point that, let's say you turn on the HVAC system and you want to perform cooling, cabin cooling, right? So when you have to perform cabin cooling, there are certain parameters the cabin cooling will rely upon, right? So there's a compressor, and then that runs the whole, refrigeration cycle. There's a heat exchanger. We'll try to discuss that all the part of it. And then at a point where it becomes that, if I have to just give you a thumb rule, it's about nearly 1.5 to 2 kilowatt is the average size of a electrical load, that is at the compressor. Most of the vehicle segments like Swift, i20, i10, or all these segments, of similar segments, have the load of the compressor somewhere about this value. All right. So this is like a 2 kilowatt would be a complete peak performance. Maybe you have kept your the air conditioning system knob to a 5, and the lowest temperature, that would be the 2 kilowatt load, right? So then if you consider, let's say that day temperature is just about 30 degrees Celsius, and you don't require a lot of cooling. So it's an average cooling. So let's consider about what's 1 kilowatt. So it's like if you run the vehicle for 1 hour, so average you consume about 1 kilowatt. Imagine that you're going to drive about 120 kilometers, and the maximum speed of possibly E2O is about 80 kmph, I believe. So let's say it drives about 1.5 hours. So it means you consume about 1.5 kilowatt. That condition says that you turn down the AC for continuously 1.5 hours, right? So what happens is 10 kilowatt means you consumed about 15% of the total battery pack energy to run the refrigeration cycle. Okay, the refrigeration would be involving your compressor. That involves also the blower, right? All the systems in place. So that is what you have consumed, about 15% of the the battery pack energy. I'm just giving an estimate number, right? It's not that exactly the same. So what happens is then your range, the vehicle would definitely come down drastically, right? So 15% would be 120 of 15% is like 24 kilometers is dropped down. So then at that day you can only get about 96 kilometers of range, right? So this is a very important thing, that the temperature of the day, and these things depends upon various different parameters. Okay, so the HVAC system's energy would depends upon let's say ambient temperature, right? So it also depends upon number of people, and there are certain loads like reflective heat, conductive heat, areas of windshield, and number of people would cause it a metabolic heat. So all these parameters would include, but majorly your ambient temperature would impact a lot. Okay, then secondary you would have number of people in the car. So because the human body does produce heat, right? When you do a breathing, we put out the heat into the cabin, so that need to be cooled down. So when you think about all these things, that it is just not a linear parameter. It is a nonlinear system which varies with respect to various different parameters, right? So like just with the calculations, we understood that, if the temperature is, let's say, 45 degrees Celsius that day, you would definitely turn the knob up to like at least like a 3 to 4 with the lowest temperature, right? So that would lead, definitely to a battery discharge somewhere up to even 25% for cases, right? So when we do all these things, we try to consume energy. So that is the point of it, right? And that's the weightage of why we need to actually perform auxiliary load studies. That you would end up giving a wrong energy, sorry, wrong range calculations to your customer, right? So that's the one point. And the other point is we should actually, as an engineer, understand what is your system limitations or system performance, its worst conditions, and all these things. And that's what it helps to understand the battery pack sizing, or like, every other components in a part of it. So I'm sort of always a little environmentalist kind of a person. So what I want to kind of put across is it's just not at your car, it's not just the range which you're trying to promise to a customer. But imagine the battery need to be charged extra, right? So it means there is a more energy consumption for the HVAC system or any other auxiliary loads. That means the battery would drain faster, and then it means you need to recharge it back again. If you have to recharge again, there's a recharging losses. It's about like 15 to 20% is your charging and discharging losses. It means when you charge a battery and discharge a battery, there is a maximum amount of losses in the battery. So that is 20%, and then you have all your losses in the grid, like the losses at the grid, and then you have a production losses, transportation losses. When you think as an engineer, when you think with your heart that anything which you contribute, even just 1%, believe me, that 1% of contribution or a system level improvement in the efficiency or reduction in the energy consumption can go a very long way, very, very, very long way. That is what one should feel and think when they work on a system. That is when somebody can understand the impact of why we need to work on even impacting about, let's say, 0.5%. If you drive that over a lifespan of a car, imagine the car drives about 1 lakh kilometers, and 1 lakh, which is 0.5, you have contributed about, decently 5,000 kilometers of, the energy that has been consumed by the car, right? That you might have reduced for the reason of this. I'm just giving you 1 lakh kilometers range for an electric car, right? So that is how we need to think, and that is how we can improve the purpose of actually moving to electric mobility. So anyway, that's the part of the GAN, and coming back to the systems in place. That let's start with the first system, that is a HVAC and climate control system. Just to see some questions in the chat box here, I will try to address them right away. Vrishabh Kulkarni, is secondary battery is auxiliary system? How to increase the range of a vehicle? Okay, is a secondary battery is an auxiliary system? Yeah, it has to be, because it has to be charged through a DC-DC converter, right? So it also becomes a part of the auxiliary load. How to increase the range of the vehicle? Okay, that's a larger question. We can come back to that. So there is a question from Sudhir. What happens when you start and stop an HVAC system continuously? So that time of design, okay, battery sizing, the start current is considered. Okay, maybe if you kind of put across the questions a little in detail, so that maybe I would be able to address the question. Okay, cool. So guys, if you have any questions, don't delay. Just drop the questions, and I will try to address them in between the slides. Cool. So HVAC and climate control system, you would know, and which we have discussed already, that this is a cabin heating and cabin cooling system. That is what is basically the HVAC climate control system, basically. So 1 second. Hey Google, cancel the reminder. So coming back to the climate control systems, we would have different type of loads here. That is what we have tried to represent as a part of this details. So there are 3 different loads. One is body conduction load, and a metabolic heat load, and then the ventilation load. So this is typically which we consider when we perform an HVAC system modeling. Powertrain energy is basically the energy from for the driving of the car. We have considered a same car. This was done on a Nissan Leaf at various different ambient temperature. Imagine you have a Nissan Leaf car and then you have a powertrain model of the Nissan Leaf, HVAC system model of the Nissan Leaf, then you can perform studies at various different temperature. Because we have a reference test data, which is practically conducted test, that the car was driven at various different temperatures like 0, -10, -20, -30, 10, and 20. Okay, so then we are trying to capture the amount of what is the range that is the vehicle is giving, and also what is the percentage of energy consumption by various systems too. So we are trying to correlate that data with a powertrain model, that the data becomes validated. The model becomes validated as a part of it. In the part of the discussions, we try to develop the studies. We were close about 3 to 4% of error percentages to the practical values. So this is something which looks as a part of the whole detailed discussion. The 20 degree was a temperature that was set as a required desired temperature, and test was conducted at lower temperature. So typically you would have your heating system that is on, right? So the heating system is to compensate all your, the loads, that is basically the metabolic heat and ventilation load and the conduction load. So if you see, there is no, I would say, conduction load and a ventilation load, because at 20 degree, that's what the desired temperature you are requiring for. That is why there is no that part of the loads. But if you see here that that's the different part of the loads, that is a comparative study what we kind of put across. So it means I'll come to that, how much percentage of the energy does this system would consume at various different temperatures. If you go lower the temperature, so the heating system consume a lot of energy to retain the temperature of the cabin at a specific value. So these are some systems which are present in typical HVAC system. This is a PTC based, HVAC system. There's one more which is by Tesla, which is a heat pump based system. Anyway, they used to also have a PTC based system. I think in still some of the cars they have a PTC based system, but now the latest models they have introduced a heat pump based system. So we understand that down the sides. So when we call it an HVAC system, there are some components that comes as a part of the HVAC system, right? The first and very important thing is your the electric compressor, which is the device, because it has to be electric one, because there is no other engine that is driving the compressor. So there has to be a motor which is inside and that drives the compressor. So it's electrical compressor. And then there is a PTC heater, which is a device which is used in the heating process. So there is a electrical sort of a setup inside that resistance of the coil would help us to produce the heat, and then you supply a specific amount of current, and that would rise in temperature of the coil. Then you pass the air over it, or if you want to have a liquid-based interactions, you could perform a liquid-based interactions too. It depends upon, there is a liquid to air interaction, air to air interaction. Different kind of PTC systems are available. That is according to your choice of system. Because in most of the cases, the PTC heater shares the path between the battery heating and also the cabin heating. Okay, so it means when it is sharing the path between battery heating and battery cooling. So if your battery heating system is liquid cooling, so the liquid-based system, right? Then you need to have a liquid to air interaction, right? So then if it's a cabin, it's definitely only the air, right? So like it depends upon how do you want to architect your system, and but the systems are available either for an air to air interaction or an air to liquid interaction or liquid air interaction. So there are some systems that are part of a if you want to talk about a battery heating, then you would definitely need to have an electrical coolant pump. And then we have obviously condenser and radiator, because after the compressor, you let the system, and then you have a condenser and an evaporator in place, and then the radiator. So this is typically what present in any system. So if you talk about a pump, to run a pump, you require energy, right? You need to model the pump, and depending upon its flow rates, what kind of load can be present on the motor, and how much of energy that can be consumed. You can model a PTC heater, and then you can check at a various different heating requirements, what would be the electric energy required at the PTC heater. Then you can perform and model the compressor also, where you will be able to understand, how much would be the electrical energy required when the compressor is running at different load conditions. Then you can perform some of these models also, the numerical models that I'm meant to tell you in MATLAB or any other software as such. So where you will be able to, build a whole cabin and then interact the cabin with the whole these component models. Then you will be able to estimate the amount of energy that is required either on the cooling side, either on the heating side of it. But though these are the systems, right? There is a fan here, then there's an electrical component in the compressor, then there's electrical component in the PTC heater, then there's electrical component in the pump also. So they all, when they run, they consume energy. The whole job of me as a simulation engineer is to estimate the exact amount of energy each of these systems will consume at a given point, at a given loading conditions, right? So that is a part of components and what we do in simulations to sort of figure out what is the load on the system. So this is a graph I might have also already showed you in various different presentations. That the SOC, we have a same car, same driver, same road condition, but the only parameter that is varied is the temperature, right? When the temperature was varied, so what happened is the SOC of the vehicle when it is stopped, right? So imagine these are the vehicles at different temperatures. If you take a -30, so the depletion of the battery temperature for the specific driving range was depleted up to about 69.5, 68.5. But at the same vehicle, at a same driving condition, at a little lower temperature, like -20, it was dropping about 69.5. It's like a 1% or a 1.5% of lowering the energy consumption. And that means increasing the SOC, state of charge left in the battery, right? If you sort of plot these graphs in place, you kind of get to know, the impact of temperature at various different loading conditions. This is on the heating side, right? So then there's also the cooling side. When it comes to the temperature goes to like 30, 40, or 50, you can also perform studies where you'll be able to estimate the amount of energy consumption at various of these temperatures. So the requirement is we should know the worst case condition. What is that going to happen when the temperature of the cabin is very, very hot or very, very cold, and this is only part of the cabin, right? And that is something, difference between 20 degrees Celsius to uh, minus 30 degrees Celsius. This is close to about, let's say, if you plot a graph, it's about 73.5. It's about 68.5. It's close about like 5% SOC, right? 5% SOC of a Nissan Leaf. The battery pack is about 26 kilowatt, I believe. I don't remember vividly. So 10% is 2.6 kilowatt, close to. And if you put this number into a place, this is possibly about 1.3 kilowatt. This is only for a specific distance. I'm not telling about it's a 100 kilometers or a 0 to 100 to 0% SOC. When you talk about, let's say we're talking about at 20 degrees Celsius, 75%, I think we have only driven about 30 kilometers of range, maybe. Okay, because how do I say that 25% of the energy is consumed, SOC is consumed for running this distance? It means it still have about 75% left, right? So multiplied by 3, it's average. Nissan gives about 150 kilometers of range for the battery pack what they have. So that is close to about, maybe they would have driven 30 kilometers in this drive cycle. Just for 30 kilometers, there is a difference of 1.3 kilowatt extra energy consumption if the temperature falls to -30. That doesn't happen in our country like India, but though it can happen in other countries as well. Right. So this is a very significant input that why we need to perform simulation studies and even real-time tests. So I want you to consider auxiliary loads as one of the prominent loads and specifically HVAC loads are the prominent loads. All right. So moving to the other part of it, which is basically a new advancements and a patent being filed in 2020, I believe, by Tesla for a heat pump based system. This is not very new again, and there are a lot of companies also except Tesla. Even Porsche does use heat pump systems, and there are a lot of other companies also. But they have filed some specific patent in an area of octavol. The way they will be able to control that. It's an octav 9 slotted 8 direction wall basically, So which is electronically actuated by solenoids, which take care of a flow of thermal management, cooling liquids from various different parts of the vehicle. The concept of thermal pump, heat pump, if I kind of go back here, the concept of this system is that you would use a battery energy like as an electrical format, output of the battery as an electrical format, and run the loads. Then you produce cooling or heating effect, right? That is a concept of PTC based system, compressor based system. When you go to a heat pump based system, right, what we're trying to do is we are trying to use the energy which is available at various different sources. I think these guys have about 16 modes of operation or 14 modes of operation. This is a course which we're trying to come up on this Friday, where we have an extensive detailed study of all the different modes of operation, components involved, very in-depth detailed study. But this is a one slide. There is about 45 slides or 50 slides to understand this one at the course on this Friday. But coming back to the discussion, so what we do in a heat pump is that we try to extract the energy from various different sources. So the mode is heating side, the other mode is a cooling side, right? So when you want to do a heating, for an example, again, the heating, whether your vehicle is static, whether your vehicle is off condition, right? Whether your vehicle is in moving condition, all this parameter, whether your vehicle is in charging condition, right? Like, because you may have to even cool the battery when the battery is charging at a fast charging station, but the vehicle is not moving at that point, right? So you have to put all these systems together to kind of come to a point that this is how my system should work. So these guys have done a fantastic and a brilliant job in sort of extracting amount of heat from various different systems to do a cabin cooling, and also to do a cabin heating, and also to do a battery heating in some cases. For an example, when you're driving the car, right? So imagine the temperature of the atmosphere is 10 degrees Celsius, right? So when you're driving the car, obviously the motor is running, right? So motor is producing some amount of heat, and there's a drive unit is called as a motor in this diagram, and PCS is called as your powertrain components, right? So you can actually take some amount of heat that is from the motor. You can take some amount of heat that is from the power electronic component system. You have to do a cooling for them, right? The vehicle is running, you have to perform cooling, and the motor and a power electronic components such as motor controller, DC-DC converter, all these components are functioning, right? So then you take some amount of heat from there, and that heat can be pumped to the battery. It means to heat the battery or to bring the battery temperature to a specific value. Obviously, the battery temperature is trying to increase itself because there is an internal reactions are going on. But though if you want an extra heat to increase the temperature of the battery, you can take some amount of heat. And sometimes there is we call as in heat from the atmosphere too. You can take that heat and then you can use that for a heating of the batteries also. And the same way, when you have to perform heating for the cabin, so what used to happen is, if you have to perform, let's go back and try to go to the little basics here. So imagine if you want to perform a cabin heating, and in parallel you want to perform battery heating, because the ambient temperature is 10 degrees Celsius, or let's say lower temperature. Okay, that time it requires cabin to heat. It requires battery to also heat up, because I want to bring the battery back to, let's say, about 25 degrees Celsius. I also want to retain the cabin about 20 degrees Celsius. That is my goal, right? Because that ambient is about 10 degrees. So you have to perform this. So the kind of thing go back is, where is the heat that is available for me to extract and supply to this system or to this system, right? So we have a motor, there is some amount of heat. Then you have a power electronics, there is some amount of heat, right? So you pass the coolant, you extract the heat, take it out, you pass the coolant, extract the heat. Then you can have some kind of an octavol, that is a system that is present in here. Then send it to a battery. Okay, then you may even club 2 points again from another system too. So then it goes like this, something like this. I'll come back to this point, what exactly it is. Cool. So then you have taken out some of the heat from here. There's also some amount of heat being produced here. Okay. Then there's an inlet and there's an outlet to a battery. This is a battery. So now there's a compressor. Now, because you have to also do a cabin heating, right? So how we're trying to do a cabin heating, the compressor is here, right? So when the compressor has to run, right? When the refrigerant is compressed, there is some amount of heat that is at the, because when you compress gas, that produces some amount of heat, right? That's how the compression will produce any heat. So you need to take the heat out. If you want to take out the heat, you would use a component as a radiator, specifically a word of condenser, that you need to bring the temperature of this component, right? If you go back to the, oh shit, sorry, that has gone, the whole image. Right, let's come back and try to draw it here. I'm sorry to just redraw these things. This is a motor and polychronic component. So some here, and then there's an octavol. So you put it here, and then it flows out of here to the battery. So then there is a other system also would let the fluid to flow through this direction. And then there can be any other system in place. So now here there is one heat exchanger. So then there is a compressor here. So then you need to use a condenser if you want to bring the temperature of the refrigerant. So then there is a component called evaporator here that is for the cabin cooling. And then there is a expansion valve here. So then you go up, then there's one more expansion valve here, right? I mean, just trying to just draw it as simple as this. Okay, then there is some walls and all these things in place. So what you're trying to do, if it is a non-heat pump based system, so compressor turns on to cool sorry, the PTC heater turns on to heat the cabin, right? So, but here you have a compressor. The compressor turns on. You get compressed refrigerant that is carrying some amount of heat, right? I hope I'm not sort of boring to anyone. I believe you're able to follow my session. If yes, please do confirm. If I'm going too fast or confusing, just comment a question over there. I'll try to slow down, right? So you get some amount of heat in the condenser. The functionality is that you have to take some amount of heat that is present in the compressed refrigerant. If it is a real-time system in a normal car like an IC engine car, this goes to atmosphere. The heat goes to atmosphere. But what happens? You will be able to capture that amount of heat, then bring that heat to a different system. That would be for the requirement of, let's say, a battery heating. This is where how you would be able to sort of exchange the heat that is present in the system to the required demanding place. So that is how, if you see as a part of this slides here, what they're trying to do in this points of the discussion, that they're trying to take this heat out and trying to supply it to a cabin. If you put a blower here, right, that's these two systems have come together. Actually, they sit next to next in the real vehicle. So you put a fan here, you blow the fan, the heat that is present in the compressed refrigerant, which is flowing through this, will kind of cool down, right? That cooled refrigerant will go here and go up to the system. If you want to perform a cabin cooling, then it goes to the expansion valve. When the refrigerant get expanded, the temperature drops down. You can do a cooling also. But right now we don't want to do a cooling. Then the flow goes here. Then the system kind of there is again an expansion valve here. If it is a chiller that comes to interact with all the liquid based system. This is a refrigerant, right? Until here it is all the refrigerant. This is also refrigerant. This is all a refrigerant based system, right? This is all a refrigerant based system. The rest everything is a liquid based system, right? There's an heat exchanger here. We call as a chiller, LCC, liquid cooled condenser, and a cabin condenser and a cabin evaporator. This part is for the cabin, and this part is to interact with all the powertrain systems and non-powertrain systems. So what we do is the fundamental concept is using the heat, all right, using the heat from a specific source in a highly effective way, highly efficient way, taking it out and using in the different part of the system. So that would be the whole interesting approach what we are trying to do as a part of this activity in heat pump. So this whole drawing representation we're trying to sort of go through here. It is not possible to understand everything in a one day. It is more than about, I think, 100 pages of patents. If somebody want to understand, it is really, really, really complicated if you don't know the fundamentals of the system in place. So, in the time when they're trying to do a battery heating, right? They are not letting the liquid to flow to any other system here. Okay. So what they're trying to do, they're just trying to heat the battery at this specific temperature. If it is minus 10 degrees Celsius, and then when the condition is ongoing, so they would do a battery heating. How they would do a battery heating? They would take some heat from the drive unit, from the PCS. They would perform the circuiting systems, and that is how they would be performed. They won't interact with any other system. So what happens when you do a compressor running the compressor? So you would, for this condition, you would run a compressor at a very different efficiencies that it produces more heat, and then you take that out, and then you do not interact with anywhere here, right? If you see that you have a refrigerant, which is basically cooler one here, it becomes a little warmer. How does it become warmer? There is a different way to warm it up from the atmosphere. So you see a radiator here. The system is trying to flow from all the way, and this is blocked. So it is going through a radiator. Radiator is interacting with the atmosphere. Basically, we're trying to take some amount of heat from the atmosphere and trying to warm up the coolant, refrigerant, and then put the refrigerant back into our own accumulation system, and then to a compressor. And this is taking care of, this portion is taking care of cabin heating, and this portion is taking care of a battery heating. So like this, there are about 16 modes of operation, like where you use this system also to cool the battery, and where you use some part of the battery energy to perform different activities. Like this, there are various combinations of it, and that is all done through this component called octavol. Okay, that is a system that has been developed by Tesla. I think that's why they have made it patented. So that takes care of all the flow controls, at all the modes of operation. So that's about the basics of the system. Right. So we have some questions. Let's quickly take the questions. What happens? What type of signals are required to communicate between the electric vehicle and charging station, and what are the parameters are required, for example? Okay, I think that may not be a point of discussion, Trilok. That would be maybe when I kind of host the session on the communication systems or on the chargers, maybe we can talk on that. So can we have a solar panel in the car? Okay, so it's a lot of things, it's a cost, it's reliability, it's a assembly, everything matters in place. So it will come maybe down the line. And the efficiency of the solar panel is also not that great today. So it may happen down the line. Cool. So then we move to our battery thermals. That's next discussion topic. So the battery thermals, until now we talked about a HVAC system, climate control, battery cabin cooling, and the cabin heating systems. We used either PTC based system, or we can use a heat pump based systems. Cool. So then we have a battery thermals, which is basically PTC based. If you want to perform battery heating, how do you do it with battery, with a PTC system? So if you see here, there's a PTC system is there, and then there is a battery, and you would use electrical energy from the battery, right, which is going out here. Then that energy would heat it's electrical conversion of electrical energy into a thermal energy by applying an application of a resistance of the materials, right? So you have a reservoir here, there's a pump, and that puts up the pressure, so that flows through the system. So this is a liquid interactions. So then it goes in here, and then you can use this to do a cabin heating. Okay. Similarly, in a way that you can run the system down to the battery also, if you want to do a battery heating, and then any of the circuits which comes across to the battery, battery heating will be placed here in the circuit. So this is how you could do, and then it flows back here. Then the whole circulation cycle involves. So you would do if it's a PTC heater, you can use PTC heater either for cabin heating, and you can use a PTC heater for the battery heating purposes, right? And average size of the PTC heater is anywhere even up to 5 kilowatt. Okay, so this battery PTC heater can even work up to 500 volt architecture, 600 volt architecture also. So you can just check out PTC suppliers across the globe. You can find some specific information. It will be very fun to learn that way. So, but though as this discussion of the topic, so there is a PTC heater can be used for battery heating and also battery cabin heating. So heat pump based system, you have only the compressor that can be performing the cabin heating. We can also use a source of energy from different components too when the system permits. Okay. So the battery thermals as a part of it. So where once the liquid comes in, so there are different paths to enter. Then there are different paths to flow in between. If you see here, right? Yeah, if you see the part of this, the very minute lines here, that there is a small pattern of holes that are present in the channel. So they carry the cooling or heating fluids. Then there is a interaction between the cell and the cooling fluids. So there is one more small thing which I kind of skipped here to mention. There is a concept called cabin preheating. The meaning of cabin preheating is if the ambient temperature is, let's say, 20 degrees Celsius, or sorry, minus 15 or minus 20 degrees Celsius. If you just directly take the car out to drive in the city, it would be very bad. It can even consume more energy. Okay, so what you can actually do, the best thing to do is you should do a cabin preheating. That means just turn on the vehicle and let the cabin to come up to a temperature of 20 degrees Celsius, which is your 20 to 24 degrees Celsius, is your comfortable cabin temperature. So this concept is called cabin preheating. You can preheat the cabin and then take the vehicle for driving. Okay, and it can significantly improve the range of the vehicle also. Okay, so that is again, you can perform some simulation studies on that too. 1 second. So if you have any questions, please do drop the questions. I will try to address. Okay, so this temperature estimation, it means how much will be the rise in temperature is what we have to understand, right? And the rise in temperature is because either the battery cell reactions or it is atmospheric temperature. There can be any minute other loads also that can contribute to rise in temperature. So cell reactions depends upon directly proportional to cell current. Cell current is directly proportional to I would say flux. Flux is directly proportional to torque, and torque is directly proportional to your acceleration, right? So if you are driving the vehicle at a very high rate of acceleration or a higher speeds, certain accelerations and things like that, it means the battery current will be increasing more, drawing more, then there is a reactions are more, then the temperature also increases. Obviously, the atmospheric temperature is high, that contributes also to increase in temperature. So how do we analyze? We perform simulation models. We build the complete cell level model where we'll be able to estimate the temperature and substitute atmospheric temperature contribution and estimate the exact temperature. See, the same car at the same driving cycle, if you drive in different road conditions, the temperature rise can be different. The same vehicle, you see here, the temperature rise is only about 2.5 degrees Celsius at a UDDS drive cycle, because the average speed, maybe it's in miles, it's about only like 12 or 15 miles, and the top speed is about like 40, somewhere about 40, 45. And then if you take a US 06 drive cycle and a highway drive cycle, right? So the aggressiveness of the drive cycle is higher. That means the acceleration values are higher. That means the temperature of the battery is going to also increase. So this is a way to understand, okay, what is the way to, we need to perform a lot of studies like this to kind of figure out, what is the load that is going to come on the battery cooling requirements as such. So again, in the same way, there is a battery preheating too. When we have to perform some studies to make the battery in a better conditions to operate for a longer life, you can perform some of the battery preheating requirements too, so that it can increase the battery life. The overall understanding is we need to estimate the temperature, and then depending upon the rise in temperature, we need to figure out, okay, whether we should bring the temperature down to a specific value, or is it okay in permissible limits. If you decide if you want to bring down the temperature, then all your systems will come into a picture. If it is a heat pump based system, is it a compressor based system, and things like that, then the whole cycle of development and components will come into a picture. So this is, I would have pretty much explained till now. I've taken a lot of time to ensure that I lay a proper foundation. I here on pretty much have simple slides in place to sort of also mention that there is a motor thermals too, which kind of have to be taken care very seriously. If you have to perform cooling, then you have to contribute some amount of energy, either at the compressor, definitely at the compressor side. So that is going to be consumption of energy from the battery pack. Similar way, we have a requirement for the power electronic cooling and auxiliary like DC-DC converter. So, in Tesla, I think the DC-DC converter, if you see, it's about like 2,500 watts. If you see, it's at 2,500 watts, right? So the meaning of that is it's a 12-volt system, 2,500 watts. Okay, if you divide, the number you get would be quite shocking. Okay, I think its maximum rated is about 200 amps. If it is carrying a 200 amps of current, so obviously there's going to be a lot of heat that is going to be produced in the system. Okay, so that means it also requires an extensive amount of cooling, right? So then the charger circuits, let's take 48 amps. So the output voltage is what are the Tesla's battery pack output desired voltage. So it will have a lot of heat that is being produced that requires cooling. And similar systems like, there's motors which is supporting the power steering systems. They consume power. Then if you consider about the braking systems as such, I think nobody would have seen these components, very clearly. If you see here that we have a lab facility in Bangalore, so where we have an access to open the whole Mindra E2 and check it out. So if you see here, there is a electrical connection to this component. This component is basically a component which is connected to a vacuum of your brake. Like if you have used a car, imagine if the car is stopped, engine is off, you try to press a brake. If you press it 5 times, it becomes so hard because there is no vacuum. Because vacuum is assisting the brake to function. Now you don't have the vacuum of the engine, so you have to have a different components like this. These components also consume desirable amount of energy. So then apart from it, there are a lot of other systems which I kind of put across all in here. They all consume energy, and that would definitely create some amount of load at the battery itself, right? So we should study all this system. If you study all this system, put a perfect detailed analysis report to an engineering team who are trying to size the battery, then they will be able to do a fantastic job, right? So if we don't do that, then we would not be doing an honest detailed technical analysis, then what system have been improvised or put into a place to make it as highly efficient. So is there a scope for career and how to acquire skills at last? So if you ask me, we are providing the programs on auxiliary systems to a lot of companies, an engineer from a lot of companies. At least about people with 3, 5, 10, 15 years of experience. At least we get about like 4 to 5 people every week. And that's close to about 20 people a month nearly, who ask for the programs on the auxiliary load systems. because it has become very critical to model these systems, also understand these systems. So Decibels has extensive courses. You can start from this point. This is a level 2 program. So once you finish this level 2 program, then you can take up the level 3 program. It is L3. This is L3. This is L2. L2 is mandatory for anyone to go to level 3. So if you take up L3 directly, there is no way to enroll for L3 because it's a request basis only. So you can start from L2. It is all done in MATLAB. So this is also done in MATLAB and the systems like that. We've been supporting a lot of engineers. There's a good amount of demand in the market for engineers with a good sort of solid skill sets in these areas of powertrain system modeling and analysis. Great. So that's pretty much from my side to sort of address this whole today's session on auxiliary systems present in an electric vehicle. The floor is open for question, and that's pretty much from my side. Thanks a lot, everybody, for participating in today's session. So as a part of the technical topic, that's pretty much from my side. If you have any questions, you can stay back and you can ask those questions. I will try to answer those questions with any amount of knowledge I have. Okay, so there is one question I was supposed to address. Sabyasachi, for battery thermals, the reservoir needs to be replenished with liquid from time to time. It definitely depends, but typically there would be a periodic service maintenance servicing that would be scheduled by a manufacturer. So if you read the repair manuals, like not a customer's detail manual, but a repair manuals, you would have the service period for which you may definitely have to replace or fill up some amount of fluids into the system. So anybody have any questions? Great, guys, if you leave from the session, so please do give a feedback on how the session was. Was it useful? Is it like, was it's really beneficial for you? I would be very glad to hear from that, and because that gives me a feedback to do sessions further. If it is not benefiting, for sure, I would stop the sessions from the upcoming Sundays. So if you feel it is beneficial for you, if you feel it has been useful for you, so please do share some of your feedbacks, and that would help me to sort of make the session to go in the upcoming weeks, or also do any improvements from your side. If you have any specific topics that you want to sort of want me to address, you can also drop the details over here. Great. So before you leave, so please do share your feedbacks, and which keeps me motivated to have in the upcoming weekends. All right. So if you have no questions, thanks a lot, everyone, for being on Sunday and spending time with me. So upskill yourself. There's a huge amount of opportunities in the EV sector. So I believe the day is for you too. And because a lot of students whom we have trained day in, day out, a lot of job opportunities we are able to see for them. And I believe it comes for you too. So with no questions on the ground here, so thanks a lot, everyone, for participating in today's session. A pleasure to have you here, and keep learning and keep making things happen for the future. So thanks a lot, everyone, for participating in this session. So guys, anybody who have questions, you can stay back. I'll try to address the session in continuation.